Hello everyone and welcome back to the Calculus Fun Room. In this video we're going to discuss the topic of antiderivatives. Now up to this point, right, in this chapter we have been discussing derivatives. And one of the things that we use to motivate the conversation of derivative, remember a derivative is a rate of change. So we initially started talking about like having a position function. So I throw a ball into the air. The equation describes the height as a function of time, let's say, and then we want to find the velocity. So we took a derivative, right? And throughout the chapter up to this point, we started to focus on a lot of the mechanics. We talked about quotient rule, product rule, chain rule, derivatives of trig functions, polynomials, roots, logarithms, exponentials, so on and so forth. So as we learned those skills and derivatives of those functions, we would then step back and look at the big picture, talk about applications. So we are going to ultimately talk about applications here. One of the things we want to begin to do is develop the process, if you will, the skills for finding antiderivatives. So again, just to kind of connect to prior conversation. Let's suppose we know the velocity equation of some particle, right? So I have a particle, it's moving along a straight line. This is the velocity of the particle, let's say, and we want to find the position. So since velocity is the derivative of position, then what we need to do is find the antiderivative. So we're going backwards, if you will. So I would look at this velocity equation and I would say, what's the antiderivative, right? In other words, what did I take the derivative of to get 3x squared? And we know pretty intuitively that that would be x cubed, right? Because when I differentiate x cubed, I get 3x squared. Right? What do I take the derivative of to get x? Well, I know that that would be x squared. However, think about this for a moment. When I take the derivative of x squared, I get 2x, and I don't have a 2 in my original equation. So what I need to do is put a 1/2 in front of that expression, so that if I take the derivative of 1/2 times x squared, I bring the power down, take 1 away from the exponent. So I would have bring the power down, take 1 away from the exponent, but I have that 1/2 sitting in front of there, and I would end up with x that was in our original velocity function. Then I look at minus 3 and I ask, what do I take the derivative of to get negative 3? And that would be negative 3x in that case. Now something else we want to point out here is we could have had some constant in my position function, and when I took the derivative of that constant, there's a 0 in my velocity function, right? Derivative of constant is 0. Anyway, so before we get too deep into some of the specifics, this is the general concept here in this video. I have a function that is a derivative, and I want to go backwards and find the function that came from. Right? I want to find the antiderivative. So let's discuss a couple things here. And the first one I want to discuss is kind of the formal definition of an antiderivative. Alright, so pause the video real quick to write the definition down for the antiderivative. So we can see that the following definition says that a function, let's call it cap f of x, is called an antiderivative of lowercase f or little f on an interval I if cap f's derivative, cap f prime, equals little f for all x in I. Now typically the interval I would be the domain of the function, but it doesn't have to be. So I just wrote down the two functions that we talked about a couple minutes ago where I had a velocity and a position. So the velocity being the derivative of the position. Now if we're going to frame this in the notation being presented in this definition of an antiderivative, what we have then is our little f is our derivative function. So we would have little f being 3x squared plus x minus 3, and then its antiderivative is the x cubed plus 1/2 x squared minus 3x plus c. Alright, so now that we've taken a look at the official definition, we've talked about the symbolism here represented in that definition, keep in mind that this is a antiderivative. Cap f is an antiderivative because cap f's derivative is lowercase f. So we're satisfying that definition in terms of our antiderivative, being able to take a derivative to come back where we started. So that's a nice way we can always check our work. If we start with a function and we're being asked to find the antiderivative, once we find the antiderivative, we can always differentiate to come back where we started. Now, in the beginning of this video, we've been discussing doing antiderivatives just any kind of an intuitive manner, right? We had 3x squared in our function, and we knew that that had to come from x cubed as a derivative of x cubed. So what we want to be able to do now is have kind of a more formal, let's say some rules, if we will, a little bit more of an efficient approach. We don't want to have to take an intuitive approach. We want to be able to have kind of all the knowledge we've discussed up to this point of derivatives and put it together collectively and look at really a list of known antiderivatives. All right, so I paused the video for a moment just to write down some of the general antiderivatives. And in the organization of the videos I'm creating, up to this point, we have now learned the derivatives for all the elementary functions, transcendental functions. So we've learned derivatives of polynomials, root functions, exponentials, trig functions, hyperbolic trigs, inverse trig functions. So let's take a look now here at a list of antiderivatives of the functions of which we already know the derivatives of. Now keep in mind, when I look at the function on the left hand side, so for example, let's look at this first entry. The first entry is the function 1 over x. Its antiderivative is ln of x. So again, we're saying basically, what did I take the derivative of to get 1 over x? And that is ln. Now obviously, I can start on the right hand side of this column, right hand side of this list. I can start in the right column and take the derivative and go backwards, right? So the derivative of ln of x is 1 over x. So again, I mentioned that because as we look at this list of antiderivatives, that's really where these antiderivatives come from, right? Is what did I take the derivative of to get that function? So when I look at e to the x, right, what did I take the derivative of to get e to the x? Well, I took the derivative of e to the x. Now I want to point out to you again here in all of these antiderivatives, I'm putting a constant. I'm putting plus c. And again, that's because I could have any constant come out of this process of an antiderivative, because when I take the derivative of that constant to go back in the other direction, the derivative of the constant is 0. Now what we're going to typically call this is a family of antiderivatives. Right? So I'm going to scribble that over here. These are a family of antiderivatives. And these antiderivatives are true for any value of that constant. So that constant could be 7, that constant could be square root of e, that constant could be pi cubed, whatever that constant is. Could be anything constant, could even be 0. Okay? But we want to discuss the most general antiderivative, and that's always going to involve some constant. So let's continue looking at this table here, right? So the next one, b to the x, and the antiderivative of b to the x would be 1 over ln b times b to the x. And again, feel free to take the derivative of the right hand side to go back to the left hand side to see where that antiderivative comes from. Right? The antiderivative of cosine would be sine, the antiderivative of sine would be negative cosine, the antiderivative of secant squared would be tangent, right? Antiderivative of secant tangent is just secant. And we have the two hyperbolic cosine functions that we're going to typically see here. We also have the inverse trig functions that we talked about. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. So then the antiderivative of 1 over square root of minus x squared is inverse sine. And then the inverse tangent, 1 over 1 plus x squared, has an antiderivative of inverse tangent. Now what you'll notice in most lists of antiderivatives, we don't write the inverse cosine. And I'm going to scribble this over here to the right. Yet if I had negative 1 over the square root of 1 minus x squared, its antiderivative would be inverse cosine of x. But we typically don't write that in a list of antiderivatives, and here's why. What I would probably do if I saw 1 over square root of 1 minus x squared, negative 1 over square root of 1 minus x squared, I would pull the constant in front, and I would write it as 1 over square root of 1 minus x squared times negative 1. So that's going to really be negative the inverse sine of x. All right. So wouldn't be incorrect to take negative 1 over the root and say that that's inverse cosine, but you won't typically see that presented in any type of solutions manual or formal conversation about antiderivatives. Now, what we haven't listed and what we're not going to list is like an antiderivative of, x squared being 1/3 x cubed. We're not going to list the antiderivative of square root of x. All of those expressions where I have x to a power, we're going to use like the power rule for antiderivatives. So that would look something like this, right? And if I have the antiderivative of x to a power, right, when I differentiate x to a power, I bring the power in front and subtract 1 from the exponent. So when I go in the other direction, what I'm going to do is divide by the exponent, and I have to add 1 to that exponent. So that would be the most general form for the antiderivative of x to some power, and that exponent can be, any real number. Right? Well, except for x to the negative 1, right? Keep in mind, if I have x to the negative 1, that's really 1 over x, and that antiderivative is log. So this property is true, as long as n is not negative 1. Otherwise, the antiderivative of x to a power is add 1 to the exponent, divide by that new exponent. And then we have some other generalized rules that if I have a constant times a function, I can, in essence, pull the constant out of the antiderivative process, take the antiderivative, and then multiply the constant back on, just like we did with derivatives. And then the antiderivative of sum or a difference is the sum or the difference of antiderivatives, just like we had for derivatives. All right, so let's take a look at a little bit more of an interesting example. I wanted to mix a couple of these different functions together. So the instruction here would say find the most general antiderivative. So we have this function, we're going to find the antiderivative. So again, mentally, this is the derivative of some function. What function did we take the derivative of to get here? So we're doing an antiderivative. Now, let's take a look at this each piece at a time, right? So let's take a look at the 2x to the 6th. So following those antiderivative rules that we would have here, that first term is I'm going to pull the constant off, and then the antiderivative of x to the 6th is I'm going to add 1 to the power and divide by that new power. When I take a look at sine function, right, if I look at that antiderivative list, so I'm going to take the negative 1 away, and then I'm going to take the antiderivative of sine, and that's going to be negative cosine of x. And again, if I take a look at that antiderivative list, right, the derivative of cosine would be negative sine. So I really have a plus cosine happening here. And again, if I take the derivative of cosine, I'm going to get negative sine, right? So that's where we're coming from there. And then this last piece. So look, this last piece is going to be a little tricky. And here's what I want to do first, right? So here's why it's tricky. This last term is a rational expression, right? I have 3x minus 1 plus root x over x, and we don't know how to undo the quotient rule. And we're not going to learn that in this section. We're not going to learn how to undo the quotient rule, or undo the product rule, or undo the chain rule. And we will learn that in the next chapter, and we'll take this idea of antiderivatives much deeper, and we'll look at applications of these antiderivatives, other than velocity to position. So in this video, in this section, what we have to do with that rational is split it up. We have to do a little bit of algebra manipulation, right? So I'm going to slide my whiteboard over just a little bit. And so what I'm going to do is take that rational expression, and I'm going to write it as 3x over x minus 1 over x plus root x over x. And when I simplify each of those, I'm just going to get 3, this is minus 1 over x. And then keep in mind what I have in that one fraction there. All right, let me take that fraction of root x over to the right for a moment. This is really x to the 1/2 over x to the 1. That's really x to the 1/2 minus 1. When I divide like bases, I subtract exponents. So that's really x to the negative 1/2 is what I have there. Now in reality, that is 1 over the root of x, but I'm going to leave it as x to the negative 1/2 because what I want to do is use my power rule for antiderivatives. I want to leave it as x to the n so that I can add 1 to the power and divide by the new power. So now that I have this equivalent expression for that rational expression, and we've written 3x minus 1 plus root x all over x as 3 minus 1 over x plus x to the 1/2. So now I'm going to take the antiderivative of each of those pieces. So what's the antiderivative of 3? That is going to be 3x. What is the antiderivative of negative 1 over x? So I'm going to pull the negative 1 off. Antiderivative of 1 over x is ln of x. And then what's the antiderivative of x to the negative 1/2? So I'm going to add 1 to the power. So I'm going to have x to the negative 1/2 plus 1, and then all divided by. So let's see, negative 1/2 plus 1 is positive 1/2. So there's my dividing by that new exponent. So let's just clean this up a little bit more. So I have 2/7 x to the 7th plus cosine x plus 3x minus ln of x. And then I'm going to go ahead and flip and multiply that denominator and write that back as a radical. Right, so I have x to the 1/2 power, which is really root x. And then to make the most general antiderivative, I need to put a constant at the end there. Because again, if I take the derivative of that constant, it's going to become 0. All right, I want to come back and take a little bit more time to discuss this whole family of antiderivatives, right? This most general antiderivative. So I want to come back and just look at something a little bit more simplistic. So let's suppose we're looking at f of x equals x squared, and we're finding the most general antiderivative. So again, I would add 1 to the power and divide by the power, and then I would have a constant. Now another way to think of this is 1/3 times x cubed. So what we really have there is a cubic function, right? Now this general antiderivative is true for any value of c. So if I think visually for a moment, I'm going to draw some rough sketches. If I choose c to be 0, here's what 1/3 x cubed would look like. If I choose c to be 1, 1/3 x cubed plus 1 is a vertical shift of that cubic function. It looks something roughly like that. If I choose c to be 2, then it's a vertical shift of the cubic up 2 units. Right? It looks something roughly like that. And if I choose c to be negative 1, then it shifts the cubic down 1 unit. It looks roughly something like that. If I choose c to be negative 2, it picks the cubic and shifts it down 2. So without getting real super detailed with, graph paper, the general concept is the most general antiderivative involves some constant. Because again, the derivative of the constant would be 0 if I checked my work there, right? So we have this family of antiderivatives is what we're talking about. For any choice of c, we have one specific member out of that family. So there might be some situations where we want only one of those members out of that particular family. One of the ways to accomplish that is to specify a particular ordered pair that my antiderivative must contain. So for example, I'll switch the color red. For example, let's suppose we want my antiderivative to have an x-intercept of 3. So I would be looking for an antiderivative that passes through that particular point. And obviously there's only one member of the family of antiderivatives that will pass through that point. I might specify some other point in the plane that I want the antiderivative to contain or to pass through. So what I want to look at next in our next example is what we would call a condition, or sometimes it's called an initial condition, sometimes it's called a constraint. So I'm going to have some extra piece of information that I want my antiderivative to contain some particular piece of information. Visually, it's going to pass through a particular point in the plane, and that is going to actually choose that C value for us. Let's take a look at an example of that concept. So the instructions would say something like, find the antiderivative that satisfies the given conditions. So the conditions are that the function f is 4 minus 3 over 1 plus x squared, and that the antiderivative must contain the point 1, 0 graphically, right? So it must meet that condition that cap f at 1 equals 0. So first let's find the antiderivative here. So what did I take the derivative of to get 4? That was 4x. I'm going to pull the negative 3 off and say, what do I take the derivative of to get 1 over 1 plus x squared? Again, if I just scroll back up and look at that list, right, that's going to be arctangent. Inverse tangent of inverse tangent of x is the antiderivative, because the derivative of inverse tangent is 1 over 1 plus x squared. Now, of course, my most general antiderivative is that I have a constant there. Now I want that function, that antiderivative, to contain the point 1, 0. So I want f at 1 to be 0, right? Now, what is f at 1? So I'm going to come back to my function, and I'm going to plug 1 into my cap f function here. So if I plug in 1, 4 times 1 is 4, and then minus 3 inverse tangent of 1 plus c has to be 0. So what is the inverse tangent of 1? Right? So that's pi over 4, right? What do I take the tangent of to get 1? So this is pi over 4 plus c. So this allows me now to solve for c. Find the value of c that meets the condition that my antiderivative passes through the point 1, 0. So I'll just go ahead then and subtract the 4 over, I'll add the 3 pi over 4 over, and I could get a common denominator here. So what's that going to be? That's going to be common denominator 4. I'm going to have negative 16 plus 3 pi. So my final answer here, right, is that my antiderivative cap f is going to be 4x minus 3 inverse tangent of x plus c, and we now have what that c value would be that meets the condition that f at 1 must equal 0. So there is my final answer. Now remember, one of the cool things about this work of antiderivatives, well, there's lots of cool things about this work, but one of the neat things here is that I can always take the derivative of my answer to get back where I started, right? To check my original function f of x and make sure that the work of my antiderivative was correct. Let's take a look at an application in this example. Remember, the beauty of mathematics is in its application. So let's take this to a little bit of a higher level now, where we apply our mechanics of antiderivatives into an application. So in this problem, we are taking a look at a ball, right, that is thrown upward with a speed of 48 feet per second. We're supposed to have the word upward in there. A ball is thrown upward with a speed of 48 feet per second from the edge of a cliff that is 432 feet above the ground. Now find the height above the ground as a function of time t. Now we know from physics that acceleration is a constant, right? So we know, since we're looking at feet and seconds, we're not looking at meters and seconds. We know that the acceleration due to gravity is negative 32 feet per second. Now remember, what I'm being asked here is to find the height above the ground. So I'm wanting to go from acceleration to position. Okay. Now, first of all, the first step we have to take here is to point out to ourselves, right, that acceleration is the derivative of velocity. So to get to velocity, I am finding the antiderivative. Right? So what's the antiderivative of any constant? That's going to be the constant times my variable, right? Because what do I take the derivative of to get negative 32t? Took the derivative, what do I take the derivative of to get negative 32? Took the derivative of negative 32t plus some constant. Now, within any application like this, we have some conditions that are going to allow us to find that constant. The first condition we have here would be our initial velocity, our initial speed. So we're told that we're thrown upward with a speed of 48 feet per second. So I know in that case that the velocity at time t equals 0 was 48 feet per second. Right? And then it's positive because I'm throwing the ball upward here. So in essence, what I have in this case is the point that will help me find that constant of integration. So I know the velocity at 0 is going to be negative 32 times 0 plus some constant, and that is supposed to equal 48. So that is going to allow me to solve for c. 32 times 0 is 0, so c is 48. So we know then that our velocity is negative 32t plus 48. Now that we have velocity, we want to go to position. So again, remember that velocity is the derivative of position. So we know that that velocity is negative 32t plus 48. So we need the antiderivative to find position. So for negative 32t, I'm going to pull the constant out. The antiderivative of t to the first power is going to be add 1 to the power, divide by the new power, and then 48t, and our next constant. I'm going to use a different letter. Let's call this capital D. And the reason I'm using a different letter is I don't want to imply that this constant and my velocity and this constant are the same. So symbolically, if I use plus c down here, kind of implying, that c is the same. So a couple different ways to handle that. Some books you'll see them subscript. They'll call this like C1 and this C2, but what I like to do whenever possible is to just use different letters, just my preference. So here is my position equation, and I have again that constant. I should have an initial condition to find that constant, or some other condition. It doesn't have to be an initial condition. But in the context of this problem, at time t equals 0, the height of the object was 432 feet above the ground. So it is an initial condition because it was at the moment that I released that object. So I'm given that the initial height is 432 feet per second. 432 feet above the ground. So my position I have here, and I'm going to go ahead and plug in t equals 0. So you can see that when I do that, I end up just getting, I get 0 squared, which is 0. 48 times 0 is 0. And I end up with just d equaling 432 feet. So my position then is, so I have negative 32 times 1/2 is negative 16. Plus 48t, and then plus my constant was 432. So if we're being asked to find the position, here is our equation for the position as a function of time. All right, now in that last application, we saw a scenario where we were technically starting with a second derivative, our acceleration, and we took two antiderivatives, one to velocity, one to position, and at each point in that step, we had some condition that helped us find that constant. So I just want to practice that mechanic in this example. Let's work through those skills again. All right, so in this problem, the question is basically find the function f of x such that it meets these conditions. It has a second derivative of t squared plus 1 over t squared, and it meets the conditions that f at 2 equals 3, f prime at 1 equals 2. So going from f double prime to f prime, we are finding an antiderivative. Now actually, before I do that, let me go ahead and simplify that function first. right? Only because the 1 over t squared I'm going to want to write, as an exponent so that I can use the power rule. So f prime is going to be, so I'm going to get 1/3 t cubed, right? Add 1 to the power, divide by the power, and then I'm going to get t, so -2 plus 1 is -1, and then I'm going to divide by -1. So I really have 1/3 t cubed, and then typically would write this as -1 over t. So the first condition I have is that, and I'm going to highlight here, f prime at 1 equals 2. So what is f prime at 1? So if I plug 1 into f prime, I'm going to get 1/3 minus 1, and all of that is supposed to equal 2. And of course, as I say all of this, I forgot to write my plus c on each of those. So let me come back, backtrack, fix my error here. So what is f prime at 1? It's 1/3 minus 1 plus c, and all of that is supposed to equal 2. So c is going to be 2 minus 1/3 plus 1. Let's get a common denominator there of 3. So see, 2 over 1, that's going to become 6 over 3. And then plus 1 is 3 over 3. So I get 6 minus 1 is 5 plus 3 is 8/3. So my c value is 8/3. So up to this point, my derivative is 1/3 t cubed minus 1 over t plus, and then there's my 8/3. Now again, this problem started us at f double prime. We have now found f prime. We need to take one more antiderivative to get to f. Now, I'm going to stop for a second, because up here in the initial function, we took 1 over t squared. We wrote it as t to the -2 so that I could do the antiderivative. But when I come down here to my f prime now, and I look at 1 over t, I take the derivative of ln to get 1 over t. So I don't really want to write this as t to the -1. Think about this for a second though. If I did write it as t to the -1, and then I add 1 to the power, and divide by the power, I'm going to get t to the 0 over 0, and that's undefined. So that should be an indication to me that the power rule doesn't work, right? So this is the one scenario where the power rule doesn't work, right? When the exponent is -1. So that's because the antiderivative of 1 over t is ln. So let me just scroll down a hair, give myself a little bit more digital paper to write with. So I'm at f prime. Let's find the antiderivative to get f at t. So I'm going to pull the constant off. What's the antiderivative of t cubed? That's going to be add 1 to the power, divide by the new power. The antiderivative of 1 over t is ln of t. And then we're going to get 8/3 t. And again, I'm going to use a different constant here. Now I need to find what that constant is. What was my condition? See, we had f at 2 equals 3. So I have f at 2 has to equal 3. So I'm going to throw 3 over there. So what is f at 2? So let's see, I'm going to have 1/12 2 to the 4th minus ln of 2 plus 8/3 times 2, and I ran out of room, and then plus d, and that all has to equal, what did we say that was? That was equal to 3 was my condition. So we had that f at 2 had to equal 3. Alright, so now some fun with arithmetic. So I'm going to have 2 to the 4th is 16. So I'm going to have 16/12. Of course, I could reduce that, and I will in a moment. And then I have 16/3 equals 3. So let's see, 16 over 12 becomes 4/3. So what I have here really is 4/3, and I'm going to get a common denominator with the 16/3, which of course it already has a common denominator there, right? So I have 3, and then I have the 4/3 plus 16/3. Then I have minus ln of 2 plus d equals 3. So I'm going to go ahead then and add the ln of 2 to the other side. And then what do I have here? 16 plus 4 is 20/3. So I'm going to subtract the 20/3 to the other side. Let me go ahead and get one more common denominator there. So that's going to really be 9/3. So d is 9/3 minus 20/3 plus ln of 2. So 9 minus 20 is negative 11/3 plus ln of 2. So that is my constant for my function. So let me scroll back up here. So back up here we had f at t equals, so we have really 1/12 t to the 4th. We have minus ln of t. We have plus 1/3 t, and then plus our constant. So I'll just go ahead and write it as ln of 2 minus 11/3 as our constant there. So there is my function f given those conditions that we started with. Now again, remember that we could take our answer, we could differentiate it twice to just check and make sure we get back to the original values that we were given up here, that f double prime at t be t squared plus 1 over t squared. Alright, I think that's everything I really want to talk about in this video. Everything we've looked at here covers all the basic concepts of antiderivatives. We even looked at an application. The only really other types of word problems you're going to see in sections like this are more applications of velocity and position and acceleration. When we get into the next chapter, as I mentioned earlier, we will take a look at other even more exciting and interesting applications of integration. So just like there's so many applications of rates of change of derivatives, we're going to see by the end of the next chapter so many cool, exciting applications of antiderivatives. Hope you enjoyed the video, and I'll see you in the next video.